Hi everyone, and hello everyone online. We can't see you, but it's great you're all here as well. So I'm very happy to introduce this next session, Energy Materials Part 1. And my name's Judith Driscoll. If you don't know me, hello. It's nice to see you all. It's my great honor to introduce Vinayak Dravid. And he from Northwestern University in the US. He's very famous. I know his name. I'm really delighted to meet him now. He's going to tell us today about teaching old materials new tricks, waste sponges and foams for energy, environment, and sustainability. So your talk is about 35 minutes and then 5 minutes for questions. Thank you.
Thank you, Judith. Good morning to our local folks here. Good day to everybody else. And part of the reason maybe you may remember my name might be something to do with my cousin more so than myself, who's, for those of us who love cricket, Rahul Dravid, second cousin of mine, so I always make it a point to say that. It's a real delight to be here. It's my first visit to RAK, and it's been exhilarating the last couple of days. And if yesterday evening was any indication, I know that I'm going to make lots of friends. I made some old friends, made some new ones. I'm really looking forward to the next few days here. Before I begin, I thought I'll share with you just one word each of really the important characters that we have here today. So first and foremost, for those of you who can read Arabic, I hope I translated it well. Thank you very much for hosting us here, and His Highness, for his generosity and for his grace. Our friend and colleague who really put me on the spot here by putting me as a warm-up act for a couple of Nobel laureates. So thank you, Tony. We appreciate your leadership and pulling people together is a really great talent, and I really appreciate that very much. And we miss someone here, as many of you know, one of the recipients of the previous awards and really a champion and a sage of Indian science, Professor C.N.R. Rao couldn't be here. Like many of us who grew up in India in the 80s, he was an inspiration. I really wanted to take a moment to acknowledge with gratitude his impact on Indian science in general, but also third world science in particular, to really provide inspiration and impetus for many of us to do what we do, especially in the field of microscopy that some of you may know was dominated by Europe and English microscopy, and some of us diversified the field a little bit. The topic I picked up a little provocative because what are the ways you can do, I'm now looking at the title, IWAM, okay, Workshop on Advanced Materials. So there are two ways to make materials advanced, correct? You advance the material, as in the case that you'll hear in the next few lectures with new 2D materials and others, novel materials. Another way of looking at is making advanced material is taking existing materials and make them different or better. And I thought that I'll just pick up on that theme because only in the last 2-3 years, especially during pandemic, we recognize there's a room and role for basic science and translational science. So much of my work in the past that some of you may know is at interfaces, surfaces, looking at advanced electron microscopy to look at defects. And now we use the same principles and understand the fluid surface interactions, but we translate them to now more practical engineering problems. And I'll show you some examples of that. So I call it teaching old materials, which are polymers, typically the ones which tend to be actually waste product. So there are many parts of the world, including, I'm sure, UAE, there's a lot of waste problem. So what if we take part of the waste and clean the waste? And that's the concept that I'll show you today. So what I'm going to show is how this waste sponges and foams can be added value. Can we activate them with a capture coating that sequesters the pollutant? And we call it a nanoscale solution or a nanoscale approach to gigaton problem. As I'll show you, the scale of the energy, environment, sustainability problem is so huge that you have to start with the premise where there's the ability to make impact. So we have to use material system structures which can be scalable, which have engineering parameters to it. It has to be economical, et cetera. And you'll see some example that I think we might have a sweet spot. Before I do that, let's look at how we arrived at this, correct? I look at, you need only 3 non-collinear points to make a stable surface, and that's your stool. So if you look at growth and progress in society, it rides on these three pillars, correct? You have the energy as a way of supply typically, but it also involves demand side of energy and transport. You have the sustainability, and here it's not just sustainability of resources, which is obviously very important in terms of natural resources, but it also has to be fiscally sustainable. I mean, feeling good about something is always great, but to be able to make a value out of it and make a business case is really important. So that's the sustainability of fiscal sustainability I'll emphasize. And third is, of course, environment that we live in. And as there are many quotes about environment. We ultimately breathe the same air and drink same water. So obviously, regardless of your economic status, those are the common denominators of a society as we know it. Just to give you a sense of scale, look at the energy per year required. These are massive numbers, right? We're looking at almost 600 million terajoules of energy. You have plastic being one of the petrochemical products. The legacy for the last couple of hundred years is almost, it's just obscene number of waste products based on plastic. Look at water as another example. You have a massive amount of scale of water. So you need a solution, a set of solutions which are compatible with that scale, right? So it's hard to imagine a microgram that we make in a lab for a very complex structure would be applicable. That's, of course, is important in order to understand mechanism processes. But in order to really deploy it, you need the ability to make large quantities, and that's a real challenge. And that's the scale of the legacy. So moving forward, I think we are in a much fortunate situation in the sense that there's a recognition of changes that are occurring environmentally, climate, and I think renewable energy focus is, but there's going to be a transition period of a tremendous challenge where we have to mitigate the situations, whether it's pollution, legacy pollution, or petrochemical, or resource use as in nutrients, as I'll show you examples of. And now the threat of microplastic is emerging, and I'll give you some examples of that. So we're looking for a platform technology we can address all of these problems, environmental challenges. And I was not sure 3-4 years ago how we would do it, but I feel extremely optimistic, as you'll see in some examples. So looking back, until about probably a dozen odd years, the American energy policy was non-existent, and it was all about consumption. I think in 2009, that started to change a little bit. And I enjoyed showing this particular slide. I know it's been several decades now, and these are all the oil companies put in together in one slide that sort of gives you an idea of part of the reason this part of the world is discussed about and talked about in the fossil fuel context. And all of these legacies for the last 100 plus years are now coming home to roost. And one such example of that is the next slide. Is oil spill. So let's start with one small example of oil spill and how one can address the mitigation of it. And as I'll show you the rest of my presentation, that all of these problems rely on ability of the surface to interact with fluid. And what is the nature of that surface interaction is really it governs. So it's a nanoscale, molecular scale features and phenomena. It's like gecko. Every bond is weak, but you have zillions of bonds together that makes the interface extremely strong. So can we design a surface interface in such a way that it can capture the pollutants selectively? And it doesn't have to be perfect. So we often say perfection shouldn't be the enemy of good enough, right? So can we do it to the extent that it can mitigate the problem? And I will show you it will. And for years, there was a sort of a sense that, okay, there's a complex problem and let the miracle happen. And this slide I enjoy showing because it really tells you what was the state of the art a couple of, about a dozen years ago. So let the miracle happen. Obviously, that doesn't work that way. So if you permit me, I'll show you one short video that's produced by the National Science Foundation based on our work that sort of set the stage as how we came about working on this problem.
10 years ago, a powerful explosion destroyed an oil rig in the Gulf of Mexico. The Deepwater Horizon well dumped an estimated 168 million gallons of oil and 45 million gallons of natural gas into the ocean, making it the largest accidental marine spill in history. The event sparked a nationwide call for more research into oil spills and their impacts on our oceans, environment, and lives. Studies over the last decade have advanced our knowledge of oil spills, resulting in novel applications of emerging technologies. One brand new technology is Northwestern University's Smart Sponge. This highly porous sponge has a nanocomposite coating of magnetic nanostructures that attracts oil and resists water. The coating can be applied to any cheap household sponge and binds with oil molecules, capturing and storing the oil in the sponge until it is squeezed out. The Smart Sponge can absorb more than 30 times its weight in oil and can be reused up to several dozen times without harming marine life. The National Science Foundation funded team says right now the Smart Sponge can be used effectively to remove pollutants and toxins in water and soil. It can also clean up smaller oil spills in a more economical, efficient, and eco-friendly manner, helping to protect ecosystems and surrounding communities.
So this is just one example of how, let's take an example of oil and water. Correct? So oil and water don't mix. When they do mix, it's awfully difficult to separate. So one version of oil and water mixture is oil spill. And there are, as I noticed, there are thousands of spills that happen every day. And some of them show up at the evening news, but most of them are not, actually. On the other end of the spectrum, there's always a minority oil in water. There's a huge produced water issue. And particularly in this region of the world, water is such a scarce resource. So ability to refine water and remove oil and other contaminants is obviously very critical. So with that as the basis, we started a program in my research group called Nanoscale Solution to Gigaton Problem. And the idea here is, can we use these old materials, which is sponges and foams? Typically, especially during the pandemic, we get so much ordering from home, and you get your iPhone or whatever product you do, and you see the packaging is huge. You have a small item of interest, but the rest of it is packaging, which tends to get thrown away. So imagine if we can use part of the packaging as an value-added product to sequester pollution, and that's what I'll show you. So you'll see the series of environmental challenges that we are addressing with this platform technology. You have the oil remediation, which I just showed you. I'll show you some very specific example of nutrients, because in agriculture, the food is going to be continuing to be important, okay, humanity. And to be able to harvest food with the minimum resources is the key. And there's a huge problem of phosphate and nitrate spillover into running waters, and that leads to algae bloom and all these sorts of problems that we are familiar with. So we are looking for a solution or technology or approach that's scalable, which is effective, and it can address the scale of the problem that exists. And they're all relying on basically the affinity. How does a pollutant interact with the surfaces? And that's part of what I'll show you in the rest of the talk. So I start with my favorite character. It's usually a neutral character, SpongeBob. And so imagine sponges. So all it's asking is, can I use a coating? So make the sponge behave a little differently. So at the end of the day, it's the interaction of the surface with the product is what you're looking for. So sponge is all typically a discarded waste product. But if you can just put a coating on it, it becomes a value added, right? If you look at the size and scale of that problem, just the waste sponge, there are hundreds of millions of tons of sponges are discarded every year, and they're in the landfill. And so we're working with NGO groups already in the last couple of years, and they're collecting these as the raw material for us to make the smart sponge that I'll show you. There are many types of sponges, polyurethane, cellulose, there are different kinds. And then, of course, we expect this delivery and the material will continue in the post-pandemic world. And so the idea is a provocative one. Can we use waste product itself as a value added to clean the waste? And oil is one, and I'll show you several such examples. So we start with two basic units, which are extremely largely manufactured in millions of tons, correct? So one is a polyurethane, very well known, discovered by Bayer, that led to Bayer Company, as most of you know. And the other is cellulose-based, which I typically help out my wife in the kitchen, and you know what we do. We use soap. So cellulose is hydrophilic, polyurethane is hydrophobic. And all we do is we take a active slurry. It's a aqueous slurry. It has graphite base. It's a graphite base followed by a nanoparticle that we choose specifically a particular pollutant. So think of it as our secret sauce, and that coating of the sauce is what attracts the pollutant. And as I show you, there are ways to improve that by biasing it so that you get the energy levels. So there's a lot of electronic structure, atomic structure phenomena as it relates to the problems of gigaton pollution. So what you see on the right-hand side are some of the components that make up this slurry. So you have not graphene, but graphitic flakes, which are exfoliated through in situ formation of metal oxide. So you get extremely fluffy, large surface area, and extremely fast production. So we can make dozens of liters in an hour, and you can imagine that the tiny amount is enough to make a product very sustainable and effective. So we call it the story of R. So what is this story of R? We start with a repurposed product. So sponges, foams, after they're used, they're typically thrown away. So instead, can we repurpose them to do the function as I'll show you? So the first R is the repurpose R. And second R is reduce. That means you're not creating a monolithic material like a ceramic monolithic, but create a ceramic coating, for example. So the coating is what that does the intelligent job. And the sponge or the backbone is the scaffold or the substrate. It's flexible both literally and figuratively. And that gives you the base, the scaffold, but the active area is the surface coating. So that's and that reduces the amount that you use. OHM in this particular stands for oleophilic, hydrophobic, or hierarchical, depending on your choice. And M stands for either magnetic or multifunctional. So what you do is basically, and I have samples if anybody's interested, I can show you. It's very easy to make. So you dip coat them with the slurry, squeeze them, dry them, and you're ready to roll. Then you expose it to air, soil, water. So air is, as I'll show you a bit late, we are doing CO2 capture directly from air using same technology. Water, which I just showed you for oil, but I'll show you for phosphate. And even soil. So you can make OHM sponge balls. They can be in the pit, which are oily pit. And there are experiments taking place by the California Forest and Fishery who are doing regulatory approval of a product, as well as US Coast Guard using soil mediation. And then you remove the pollutant, as in the case, as I showed you with oil, you just squeeze the oil out, and it's very selective. So there's less than few percent of water goes in. So normally that would be a big problem, because if you have oil and water mixture and you're resulting in an oil and mixture, you still have the same problem. But here almost 95+% is recovered as oil, and that gives us only 5% water. So you recover that and you reuse it. And that is a paradigm shift, because in the past, all the oil spill and all the technologies are one use, just like our plastic, one-use plastic. And those are called sorbents. But now this ability to recover oil and reuse it 30 times, suddenly you have 1,000 times less waste. You have 1,000 times less inventory. And that becomes a commercially potentially viable approach. So that's the OHM sponge story. It's very economic because we use carbon and iron-based system. Foam is already cheap and discarded. Very efficient, as I showed you for the oil case, and very eco-friendly because it's all aqueous. There's no organics involved. There's no disposal issues and so forth. So that is one case. And does it work for everything? So there's a bunch of plots there in the paper if those of you are interested. The top left is all types of oil, refined oil, non-refined. They still have affinity. So we are looking at hydrophobic interaction between the graphitic base and the oil. On the right-hand side, you see the pH level. So regardless of the type of pH, acidic versus basic, the ability on the y-axis is the ability to absorb oil is 30 times, 25 to 30 times. Bottom left is cycle. So if I use the first time, I get certain amount of oil against water. I squeeze the oil out, I reuse it. And you can see it's almost constant for dozens of cycles. So this ability to reuse really changes the paradigm on this pollution remediation. And the bottom, the last one on the bottom right is at a different salinity, because a lot of spills occur in oceans and seas, different salinity. And as you can see, regardless of the salinity, this seems to work. So there are two parts to this. One is the technology. You don't need to understand it to deploy it and make use of it. That's one part. The other is, of course, we need to understand it, and I'll show you both aspects of this. So this is the challenge. It looks too good to be true, right? I mean, you can remove oil. It looks like a fantastic way. And there's, of course, more to it than meets the eye. We want to make sure we understand, characterize, test, and actually do deployment. So last year, we did a lot of deployment with Coast Guard and other agencies in America called ICOPAR. It's the International Consortium of Oil Spill Remediation. So now let's come back to Earth. Like we're going with the gigaton problem to now molecular scale problem. How does this happen? How that coating on the surface of polyurethane can do the wonders that I seem to show? So there are a lot of challenges. I'm originally a microscopist, and microscopists, we typically go take a problem and go deeper into it and create more problems, right? And that's how typically academics works. Here we want to do the reverse. Is we want to understand, and then based on that understanding, can we scale up the solution? So one is to be able to make sections so that we can look at that interface very carefully. And for that, I'm doing a shameless plug of the center that I've built over the years at Northwestern, which is all the microscopes, spectrometers, a lot of capabilities to analyze at the molecular level all sorts of phenomena, both static and dynamic. And the one we typically use at the left is the EPIC, is electron probe instrumentation here, where we actually will show you in situ work to be able to see what happens in actual liquids as the phenomena occur. And then as you can see in the length scale challenge, correct? You're going from a macro scale to molecular scale. So you on the left-hand side, you see the physical picture of the sponge. Then you see the network structure with the scanning electron microscope at the micrometer scale to sub-micrometer scale down to molecular scale. And so that gives you a sense of hierarchical organization of this. And this is a polyurethane case where it's uniform porosity. There's a percolation. And cellulose, on the other hand, you'll see it's a hierarchical architecture. And then what you see on the left and the right is slight difference, correct? So on the left-hand side is before coating, right side is after coating. So all you're looking at is a tiny amount, so less than 5% by weight or any other measure that you can think of. So 95 to 99% of the material is a discarded sponge. It's only the few percent that does the job is the coating. And it's a very thin coating, is adherent, and there are other challenges I'll be happy to elaborate later. And then we do multimodal. So here we want to understand not only the coating, its effectiveness, how it is, what are the different architecture of the coating, what material system it is, and how does it correlate with other techniques. And we do cross-correlation with electron microscope, optical, in this case, the Raman, because Raman is a good signature of the type of structure, chemical signature that we have in this case. And can we make in large quantities? So this is a very simple flow reactor system. So as you can see, we can make enough of material, and you remember it's only 5% that makes it an effective sponge. So if I have 100 units, I have the potential to make 500 more units of the final product. And what you see on the bottom are some of the examples. So last year was the Mauritius spill, some of you may know. In fact, late last year was the Southern California spill in Huntington Beach, and that's where some of our products actually, as we speak, are being tested by the California Fishery and Wild for regulatory approval. We're at the final stage, so in the event of another unfortunate spill, our product will be readily available. And if you look at the way the fossil fuels are here for the next several decades, and they're going to get transported. And in fact, with the climate change and the Arctic routes becoming more available, there's a much more risk of this oil spill occurring in Arctic circles as well. And that's where I think we also conducted studies with US Coast Guard that we can actually do the sequestration at cryogenic temperature, at very low temperature. And that's why the sponges seems to be an extremely effective way at all temperature to capture the pollution. The other reverse problem is the oil spill. Again, this happens occasionally. It's not how you can run a business, correct? It happens accidentally once in a while. But there's another set of challenges in produced water. These are situations where the oil is minority. It's only a few percent or a few hundred ppm. And you cannot dispose that in a typical disposal way. You have to remove the oil before you can. There are a lot of regulations throughout the world about it. So produced water is a real challenge. It needs to be done in an economic way. And this is a problem in the Middle East as well. As a lot of contaminated water, how do you purify it effectively using cost-effective methods? So this is an example, again, the same basic idea that instead of polyurethane, which repels water, here is cellulose, where it allows us to flow water through in large quantities. So we are talking about hundreds of thousands of gallons passing through the sponge-based system that we have, which is based on hierarchical structure, in this case, cellulose. And still, the same coating captures the oil and recovers it. So this is an example of a minority oil contamination in water as opposed to oil spill. Then moving forward, this is just one example of oil, and it occurs again at the interface between our coating and the fluid associated with it. So we're now trying to understand in situ as to how water and oil get sequestered, phase separated at the nanoscale using imaging techniques, spectroscopy technique. So this is just an overview of different methodologies that are being pursued in our research group. So our approach in our research group is to address global problems such as this oil, for example, separation, but it's rooted in the basic science of how surfaces interact with oil-water mixture and what are the molecular bases for the sequestration. So we work with folks who do molecular simulation, modeling. A lot of these are many details that I won't get to present today, but you hopefully can get the big picture. That it's the nanoscale approach of molecular scale interactions that's scaled up at the macro level using a sponge-based platform. So just a quick couple of slides just to show how this goes. So we can do typical studies of wetting angle measurement, but also do it in situ while we introduce water-oil mixture in an electron microscope. These are called as environmental SEM, very classic ones. So we introduce water and oil and other relatively high vapor pressure products. And you can watch the microstructure evolve in interaction of the fluid with surfaces. And you glean a lot of insight as to what is the role of curvature, what is the role of asperities, because it's a very complex undertaking. You have sharpness of edges and corners in sponge, you have surfaces, you have different length scales involved, you have capillary effects. So it's a very dynamic system, and it works remarkably well despite all these challenges. So you can watch and learn some of the kinetic and sequestration information for oil-water mixture using this type of in situ work. So that's the oil part, which is not as sexy perhaps for some because that's sort of a transition going from non-petrochemical to renewable, but in the foreseeable future, the challenges are going to persist. Another set of challenges that we had a great success last year is using the same basic platform of sponge or foam, but now sequester nutrients. Phosphate is one. This is a beautiful article by Julia last year in Atlantic about the phosphorus is the bottleneck of life. As most of us know, nitrate is another problem that you know, but nitrate at least has a nitrogen cycle to fix it. So there's a gaseous nitrogen that's way to equilibrate the ecosystem. But phosphorus is non-renewable. It comes from rock. And once you use it, you cannot reuse it unless you recover it. And by every indication, there are only a couple of 100 years of supply of phosphorus. And it's the backbone of our DNA. So, I mean, we have to have phosphorus for life. And that's the sort of a challenge that has been posed here. So one end of the spectrum is we need phosphorus, but typically when it's used in the agriculture, there's rain, there's runoff, and those go into waterways and lakes and oceans even. So there's a huge algae bloom problem that many of us are familiar with, right? And that happens eutrophication. So all the oxygen is sucked out by the algae, and all the fish and fauna underneath is compromised. And there are many examples throughout the country. I'm quite sure UAE must have some example of algae bloom as well. So how do we now address the same problem, but in a different way? So again, we come back to our story of R. So here, it's no longer a physical adsorption of oil that we are looking at. We are looking for some strong chemical affinity for phosphorus. And as I'll show you, ion-based systems are awfully good, but some little bit of promoters. Again, very cheap material that we can use for coating to sequester phosphorus. So how do we do that? Here now, instead of polyurethane, which repels water, here we want water to pass through. So we use cellulose base. All we do is dip coat it with a slurry. It gets there. All right. And we call it, student Stephanie called it a pearl membrane. So every student needs to have an acronym. So OHM was the oil, pearl is phosphate elimination and recovery, very lightweight membrane. And the idea is very simple, that magnetic nanostructure, these are basically metal oxide nanostructure coating. They have very high affinity for phosphate under certain conditions. And so what we do is we use a particular condition as in the pH, low pH, and you sequester very selectively very high amount of phosphate to the extent that it was impossible for us to believe first. But then we repeated it many times and before we published it last year, and its paper has been nominated for a prize by Proceedings of National Academy. And then you use a higher pH to recover the phosphate. So imagine, just like in oil case, we are squeezing the oil out and reusing it. Here, instead of a physical squeeze, here it's a chemical, it's a pH-dependent process. So imagine a bunch of sponges. In fact, we are doing testing in Florida and other locations where there's this phosphate ponds. As some of you may remember, last year there's a risk of a pond being close to being breached. And there was a lot of concern in Florida about this excess phosphate being released in oceans. And so here we have a low pH, absorb phosphate, high pH, release it, and you keep on doing that. And that's the idea behind the phosphate recovery. So how does that work? So these are the actual data. On the y-axis is the percentage capture. So you can see almost 100% we can get. So given a unit, this is done with purified products first, and I'll show you the actual result. We did it with Chicago Water Reclamation, which is the largest water purification facility in the world. So as you can see here, at low pH, you get very high capture. So that's one part. And at high pH, you release. And you notice the release is not 100%, it's about 70, 80% in the first cycle. That's because it forms two different types of bonds. The phosphate forms a phosphate bond, but also phosphide. And the phosphide bond is more covalent, more rigid. It attaches to the nanoparticle. And the subsequent adsorption is the phosphate absorption that can be recovered. So you see this amazing story, and then you'll see the repeat experiments. And if you look at very carefully, the first one, you notice the deep dark blue is high sequestration. The green is release, and you can see the first cycle it releases only 70%, which is nothing to be ashamed of, but it's amazing to be able to even get 70%. But you see the second, third onward, you're getting almost 100% recovery. So this is very analogous to in the battery literature, some of you may know, SEI, solid electrolyte interface. Once it forms, then it becomes stabilized, and then subsequently, if you can manage the SEI layer, you can keep on cycling the battery. Same basic idea now for phosphate remediation. And it's a hierarchical structure, so as you can see, there's a different level of porosity, so you want hydrophilicity, so water flows through, no problem. And what you see in the cross-sectional ultramicrotome with you can see very thin coating, right? And this is the coating of our metal oxide promoted. So again, basically iron-based system with some promoter that gives you affinity for phosphorus. And you can see the small portion of that. You expand it in a transmission electron microscope. You can see the coating, bright field TM, dark field diffraction, all the spectroscopy. So those are all inside baseball details. But we form a very tight surface interface associated with this, and that's specifically targeted for phosphorus, and I'll show you how it is. So now we understand why is the work that we do. So we do spectroscopy to understand energy transfer. So when the phosphate is attaching to nanoparticle, what energy transfer processes are taking place? Are they reducing the energy of the overall system? That's how things work, and et cetera. And what you see on the left-hand side, the iron 2p edge, this is the XPS work. And what you can see before, after adsorption and desorption, there's difference. Before and after, you go back to the original, but in between is the phosphide bond. In the central portion is the phosphorus signal. So you can see the phosphorus before, after, and compare it with the phosphate signature. On the right-hand side is the oxygen, which is obviously a little complicated because oxygen is common to multiple elements. But this underscores some of the observation that we see, that initial sequestration is only 70% because it forms the phosphide bond, but the subsequent is almost 100%. We also look at association. So how do we know that this is the actual nanostructures are doing the job that they are? And remember, there's a lot of precedence of using ion-based system for phosphate recovery, but they are done in a very haphazard way, which is using powder, and it's impossible to manage powders in a massive quantities, right? But having a sponge as a platform, you don't have to worry about spillage or anything. So there's less than 0.2% is recovered. And then here is the energy loss spectroscopy, where you look at iron and phosphor association, so you know exactly why and how these things are working. And last, the proof in the pudding. So we actually conducted experiment using large scale at the Chicago Skokie water supply, reclamation district. So this is the sample literally from the third stage of the purification of water, where they use biological and other means to remove phosphate. And what you see here is every other ion is exactly the same, correct? So you don't want phosphate removal, but in the process you remove fluorine and all sorts of other useful minerals that we have. What you see is only the phosphate. It's very selective, and as you can see, it's of great interest commercially. So this is a second example of how we are now recovering phosphate using pH as the proxy. You can imagine now we are extending this to heavy metal. So there is a slight change in the coating. I know Sammy and others are doing this work, and we'll be happy to share our results and details. And what you see is, again, a pH-dependent sequestration approach. So we can not only capture lead in this particular case, but we can release it, almost 94%. And so you can reuse this. And again, reuse is the key for all the approach that we are making. Microplastic, another, you can give a separate talk on this. We just submitted a major initiative with National Science Foundation, because the microplastic is a real challenge, because it is a vector for pathogens, among other things that most of us know. It turns out that a sponge with the porosity and the conductivity is an amazing way to capture based on electrostatic interactions. So electrons have become cheap now with renewable electron, and actually we're working with a company which makes washers, as in single source plastic is actually washers. And so if you can capture the microplastic as they exit the water, and that's what we're trying to do. And this is working remarkably well. Last but not the least is CO2 capture. The same basic idea of sponge and the coating can be tuned so that there's a high affinity for CO2. And while it captures CO2, we have in situ catalysis, so you can use CO2 as our basically feedstock. So Ted Sargent, who just joined us from Toronto recently, we're working on a lot of these ideas that once we get the pollutant, as in the case of CO2 as a pollutant, although it's not literally a pollutant, but the idea is use CO2 as a feedstock and to catalysis, electrocatalysis, convert that to higher carbon chain. So this sponge-based platform seems to be a very effective approach. And what you see on the left-hand side are the pollution of the pollutant, the scale and the scope that we have seen: oil, nutrients, heavy metal. And we have an approach which is sponge-based approach rooted in this interface, tailoring of the interface surface. The fluid surface interaction is what gives rise to this capability. So again, the story of R, to remember, if there's one thing that you could remember out of my talk, is this ability to reuse is what's making the impact. And this is our little team and a lot of support systems. So with that, I want to thank everybody for their attention. And a few questions. Oh, sorry.
We're running just a little bit late now, so we just have one question, Mohammed.
Thanks, Vinayak. Great talk, very elaborate. I have just one question, maybe I missed it. You use these foams that are porous. Can you elaborate on how you coat your films into certain particles? Because when you do this cleaning, you can also have those nanoparticles leaching. And also, what is the importance of surface area? Can you give us an idea about what is the porous and surface area of these materials, and if there is room to improve them?
Yeah.
And one last question is the carbon capture. One of the challenges is the capacity, and when you talk about direct air capture, is 400 ppm. How do you manage actually to have a high quantity of the CO2? I think too many questions, but
yeah. So I'll start the last one first very quickly. I think the beauty of the last approach is we don't need to worry about capacity if we can make use of the CO2 capture downstream right away. So the idea is to create a fluid based on CO2 excess and use that fluid to catalyze it so that you don't have to use surface as just this catalysis.
So in this case, you are talking about, because you mentioned direct air capture, the concentration is very low, so you need high affinity to absorb that CO2 first.
Correct. So the one that we have is a graphite base, has a very high affinity for CO2. And when it captures CO2, you have moisture swing. So it forms a carbonic acid. And we use the carbonic acid as a feedstock with a local catalysis, so you can convert that. So you don't have to have a stationary reservoir of CO2.
So you have a continuous flow.
Yeah, you have a continuous flow. So that's one. Coming back to how you make them, it's very simple. I grew up, as you know, in India, and one way they dye the sari, D-Y-E, dye the sari, is literally you dip the white cloth in the diluted solution, you squeeze it, you do it a couple of times so you get uniformity, and that's it. So it's a very cheap, effective way.
So you are saying when you create your oil, there is no leaching at all whatsoever?
Yeah, so there are two parts. So in polyurethane is a very weakly interacting system. So it will leach in polyurethane, but not in cellulose. So for phosphorus one that I showed you, we had the same question from one of the reviewers, saying how much leach? It's less than 0.2%. So I think that also underscores the role of sponges and foam as basically a scaffold. It's just a carrier And it is flexible, it allows water flow, so it has all the beauty. One last thing I didn't get a chance to mention is we are now integrating synthetic biology within the sponge. So both using organism and cell-free assay. So we can actually detect presence of lead and arsenic using a colorimetric signal, using a RNA that's embedded within the sponge. So there's it opened up unusual.
And how about the surface area importance? Do you need high surface area or
It's
not
a
really?
great question. So part of the challenge here is whatever is the porosity that we live with. So it's not as important as in the case of, say, MOF and other types of structures. So in fact, with Omar, we are actually using the same basic idea of sponge, but now coating would be of MOF coating. And if MOF acts as a sorbent, then this is the best way to actually absorb selective pollutant. And you don't need much. You don't need to have a large amount of MOF. All you need is a coating of MOF. And so I think there are a lot of subtleties, I'm sure, but at least we're in the right direction, I think. Yeah.
Okay,
Okay.
I think we're going to have
All
to
right.
thank
Thank
Professor
you very
Dravid for such a wonderful and interesting talk, and there's so many questions.